Hi, I'm Kajal Kumari, CSIR SRF Research Scholar, working with Professor Mayank Goswami, Department of Physics, IIT Roorkee. In this video, I'm going to discuss present my recently accepted research article titled "Relative Estimation of Scattering Noise and Electronic Noise of a Radiation Detector." Here is the outline of the presentation that we will talk in this video step by step. The fundamental instrument to detect radiation is radiation detector. The information of measurement is obtained in the form of spectroscopy. To analyze the measurement data accurately and precisely, one may expect minimum noise present in the measurement data. But the detector itself contribute two main factors of noise. One is scattering noise and the other one is electronic noise. The scattering noise is due to the type of the crystal material and the size of the crystal material, and the electronic noise is due to the electronics attached to the detector to detect the counts using the detector. So in this study we will find out a tool to estimate the electronic noise as well as scattering noise, and a methodology to decouple these noises. This study comprises 4 different types of radiation detectors that are sensitive to gamma radiation. To study the effect of type and size of the crystal material on scattering radiation, 4 different types of radiation detectors of different sizes are utilized in the study. To study the impact of the type of the electronics on electronic noise, 2 different types of electronics are used. Sodium iodide HPG and LABR3 are connected with distributed electronics, while cesium iodide is connected with integrated circuit electronics. In integrated circuit electronics, the scintillation crystal material coupled with a photodiode, preamplifier and analog to digital converter all are integrated onto the same silicon chip. This table shows the specification of the radiation detector used in this study, and this is the energy spectrum of cesium-137 gamma radioactive source detected by these 4 detectors. Gamma ray computed tomography is utilized as a tool to estimate the scattering counts present in the photopeak region of gamma spectroscopy. Transmitted computed tomography is utilized, so the presence of the scattering act as an unwanted noise due to unable to remove it in the photopeak region or not correctly model the scattering path in the CT reconstruction algorithm. These are gamma ray CT experimental setup used for a different type of detectors, and this is the schematic diagram of CT scanning geometry. To avoid the scattering in measurement due to the presence of the neighbor detector in scanning array, a single detector is used to perform the CT experiment. So for this, an innovative scanning scheme is utilized that will create more virtual detectors using a single detector by translating it to different detector positions in the scanning array. Here is an animated example of the scanning scheme utilized to create more virtual detectors. So in this way, it creates more virtual detectors and collect data at different angles. And in this is the real experiment in which the detectors single detector is used to create more virtual detectors and perform the experiments. To estimate the electronic noise, standard deviation parameter is utilized. This gives the standard deviation of repeatedly measured data in the absence of the object. While for the estimation of scattering noise, a mathematical tool named Kanpur theorem is utilized. Before this, KT first is utilized to only estimate the inherent noise in the projection data of CT. This inherent noise can be made up of electronic noise, system noise, statistical noise, reconstruction noise, and scattering noise. The system noise and the statistical noise is minimized using statistical rich data measurement method, while the same reconstruction method is used throughout this study, so it will not impart any effect in the variation of inherent noise. So the main component of the inherent noise is basically electronic noise and scattering noise. We expanded the scattering noise into its subcomponents, which is due to the scattering of the radiations within the radioactive source itself, within the object crystal material of the detectors. The other contains due to the adjacent detectors or shield if someone is using in the experiment, and due to any filters or grid used in the path of the radiation. Since in our experiment no grid shielding and adjacent detectors are used, so these parameters can be neglected. And we also did not the thickness of the radioactive source used in this study is very small as compared to the size of the object and crystal, so we can also neglect the scattering inside the radioactive source. These so uh, so these approximation transform the equation 2a to 2b. So the scattering noise will be mainly due to the object and the crystal of the detector. Before this, KT first is not utilized directly for the estimation of scattering noise. The more detail of the KT first and how it is working can be studied in this paper, so one can read it. So before this, KT first is not utilized directly for the estimation of scattering noise. So first, before utilizing this in this study, we will verify its sensitivity towards scattering noise. So for this, we adopted two strategies. In strategy A, we know the scattering radiations is minimum in the photopeak region as compared to the Compton region and full spectrum region. While in the strategy B, the increase in the size of the crystal material will increase the probability of interaction of gamma radiation with the detected crystal in the form of photoelectric effect and as well as Compton scattering effect. So these theoretical facts are tested using KT first to verify its sensitivity towards scattering noise. So here is the result of the strategy A, and this is the goodness of fit of RMSE, which reflects the inherent noise calculated using KT first. And we observed that for sodium iodide detector, relatively low inherent noise is observed in gamma photopeak region as compared to Compton region and full spectrum, and this is the same, and the same trend is observed in the case of cesium iodide detector and HPG detector. This is the result of strategy B, which shows with the increase of the crystal size of the crystal material, the level of the inherent noise is also increases. So these both strategies verify that KT first its sensitivity towards scattering noise, and this is the result of electronic noise. It shows that and it shows that the detector connected with integrated electronics has relatively low electronic noise as compared to detectors connected with distributed electronics. Up to now, Up to now, we are measuring inherent noise due to electronic noise and scattering noise both. To decouple these noises, we compared the pattern of the inherent noise and electronic noise, because the scale of the inherent noise and the electronic noise is different, so we cannot simply subtract the electronic noise from the inherent noise to obtain the scattering noise. So we compared the pattern of these both noises. If the electronic noise is dominant or have equal impact as compared to the scattering noise, then the pattern of the electronic noise and inherent noise should be equal, but it is not. We can see in a figure first and second. So these results suggest that the inherent noise is dominant, is scattering noise. So the variation in the inherent noise is mainly due to the scattering noise, and we can say the inherent noise as a reflection of so we can say that the inherent noise reflect the scattering noise. So afterward, KT1 is used to estimate the level of scattering noise in all the detectors used in this study, and this figure shows the level of the scattering noise present in the photo peak region detected by cesium iodide, LABR3, sodium NaI, and HPG detector. It is observed that a minimum scattering noise is observed, minimum inherent noise is observed in cesium iodide. Minimum scattering noise is observed in cesium iodide detectors, and the parameters that impact the scattering noise are given in this table, which are crystal width and the crystal thickness, and the mass attenuation coefficient, which means the type of the crystal material. These values and the scattering noise is fitted in an equation, and with an RMSE of 2% of fitting. So the significance of this equation is that the scattering noise is depends dominantly on the type of the crystal material as compared to the size of the crystal material, and we also fitted these vectors into a surface plot, and this is the error bar corresponding to each point. Up to now, we demonstrated the quantity of the scattering noise present in the measurement data detected using different radiation detectors. To see its impact on real application, we compared the CT images obtained using different detectors. This is the Cyber Phantom, and this is the simulated reconstructed image. The scanning object is made up of 3 different materials. This one is acrylic, and this one is aluminium cylinder, and in the middle of the aluminium cylinder a iron cylinder is inserted. So in the simulated data, no real data is used. So the error is mainly due to the reconstruction noise, reconstruction algorithm that is equally present in all these real data CT images. Since no real data is used, so there is no scattering noise in the simulated reconstructed CT image, and these are the CT images obtained using cesium iodide detector, LABR3, NaI, and HPG. The impact of the scattering noise can be seen in the form of the efficiency and the lack of the informations available. These are marked with yellow and red colors. So the impact of the scattering noise is observed in the form of the patches and the shift of the informations, which is shown here with the yellow arrow. So for the Qualitative estimation of scattering noise dissimilarity coefficient is used, where D1 is the dissimilarity coefficient of all over the image, and D2 is the similarity index, which is compared in the part of perspex material only, by removing this aluminum and iron part. The value of the result of the dissimilarity coefficients are in good agreement with the results obtained with KT first, and we can see a relatively low patches are is observed in cesium iodide detectors, and we have seen that in the previous slides a relatively low level of scattering noise is observed in cesium iodide detectors. So we can utilize these parameters for the estimation of electronic noise and the scattering noise. Thank you.